Welcome back to another Q&A session of Space Nuts. I'm your host for this American summer and Australian winter, Heidi Campo, and joining us today to answer all of your questions is Professor Fred Watson, astronomer at large.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Fred, how are you doing?
Oh, pretty well, thanks, Heidi. Nearly as well as I was the last time I saw you.
Oh, inside jokes. For those of you regular listeners, you know what's going on.
Yeah.
All right.
Because you were a bit under the weather before.
I am. So if you guys hear my voice sounds a little bit scratchy, I apologize. I was doing some traveling recently and I probably picked up a little germ at the airport, but that's I'll be okay. I think I'll survive this time.
Hopefully,
yeah. I don't know. I guess you never know. Could be didn't, like, you think about those crazy cases where it's like, didn't Bob Marley died from skin cancer? And it's like, I guess you really never know.
that's true.
Well, hey, here's something that hopefully you can answer for us, Fred. Rennie from sunny West Hills, California asks, theoretically, if an observer scientist outside our universe was able to look into our universe, would that observer's research on light speed and other phenomenon match our scientists' findings?
It's a great question. Rennie's one of our regular questioners and always asks the provocative ones. I like it very much. So we've got to envisage an observer that's in some other universe where the light speed and other fundamental quantities, speed of light, mass of the electron, things like that, they might be quite different. So you would have to basically think outside the box. We're talking now about the biggest boxes that could exist if we're talking about separate universes. You'd have to look into our universe and use yardsticks that were basically part and parcel of our universe in order to measure those fundamental quantities. So you'd need to have a way of determining distance, and that way you could perhaps use a way of determining time to determine the speed of light. You might well be able to determine that the speed of light in our universe was different from the speed of light in your universe, which will be a very interesting property. And it's actually one of the reasons why people speculate, Heidi, that there might be other universes. The fact that those physical parameters in our own universe are so well suited to the formation of stars, galaxies, planets, stability that would allow molecules to be created that could eventually turn into living organisms. One of the reasons astronomers think there might be other universes is because those properties of our own universe are so well tuned to life that maybe there are other universes where that is not the case. And so if you were standing in one of those universes and looking back at our own, you might well say, well, that's ridiculous. The speed of light there is only 300,000 kilometers per second. It's much faster than that here. So, you could be looking at different parameters. So I think, Rennie, it's an interesting thought experiment. And thank you very much for the question.
It's very interstellar when he goes into the dimension where they're looking through a different plane. Our next question is from Dean. And Dean says, I believe you all had mentioned previously that in a protoplanetary disk, heavier elements reside closer to the star, which is the reason the interior planets of our system are, quote, rocky. The protostar is too hot for volatile materials to become solid, and the solar wind blows the lighter elements away. My question was Earth in a belt of protoplanetary disk where liquid or water orbited? Could such a belt exist in protoplanetary disk?
This is another great question, and I suppose what Dean is saying is there a Goldilocks zone in the protoplanetary disk? Because the protoplanetary disk is where the planets were formed, and yes, the temperature of material in that disk will vary. It'll be much hotter near the star itself, and much colder outside, and we do see. Just in the way the planets of our solar system are distributed, with the 4 rocky ones internally, and then the 4 gaseous ones and icy ones further out, we see that effect of the Goldilocks zone. So Mars sits just within the sun's ice. What's it called? The ice limit. Can't remember. Anyway, it's something like that. It's where water ceases to be a vapor and becomes ice. So beyond the orbit of Mars, things basically freeze if you've got water vapor, and that is thought to be why the gas giants grew so big. The 4 gas giants, because the fact that their water is actually the commonest 2-element molecule in the whole universe. So if the water vapor becomes something solid beyond that ice limit, then you're going to get the collection of much more mass in a planet that's being built by this process of accretion. So because the water is now in a solid form, you can build a much bigger planetary core, and that is why that you can then get something big enough that it actually hangs onto the gases surrounding it, and you've got a gas giant. So that's the picture that we imagine is the way planets form. So just turning to Dean's question, was Earth in a belt of the protoplanetary disk where liquid water orbited? It wouldn't have been liquid because you can't have liquid in a vacuum, but you can get water molecules in vapor form, basically, or in the form of ice. And yes, there would have been a step there, I think, in the protoplanetary disk where the ice solidified, where you've got solid ice. So I think that's a really good question. And I believe I've seen some papers recently which suggest that we are actually observing that. In fact, very recently, I think it might even have been last week, Heidi, there was a paper that reported the detection of ice in a protoplanetary disk. So that's one to check out. It's there, and in the inner regions, it's probably too warm for it to exist as a solid material.
So Dean's on to something. We get a lot of really smart people who follow along this show too.
Let's take a break from the show to tell you about our sponsor, Incogni. Now, if you've been overwhelmed by a barrage of spam calls and emails and targeted ads, robocalls, it's probably because they can find you online very, very easily and just harvest your contact information. If you've ever felt like that, then the answer is Incogni. What happens is data brokers collect and sell your details, leading to an endless array of spam and other potential risks. And if you want to get rid of that, Incogni is the answer. It's your personal data removal assistant. It automatically sends removal requests to over 210 data brokers, ensuring your information is taken down. You can even watch the progress of it through an online dashboard. With weekly updates, you can track the cleansing of your digital footprint. Plus, there's a 30-day money-back guarantee, so it's risk-free. It's called Incogni. Take control of your online presence. Visit incogni.com/spacenuts. And here's the kicker: 60% off if you use the code word spacenuts. That's incogni.com/spacenuts. 60% off if you use the code word spacenuts. Enjoy a peaceful online existence without digital disturbance. Now back to the show.
3, 2, 1.
Space Nuts.
Our next question comes from Ron. He says, hello from upstate New York. Ron, that is where my husband is from. I wonder if you're from the Catskills area. Beautiful place if any of you guys ever get to visit. Hello, Ron says, hello from upstate New York. I was wondering, with the extreme lifetime of red dwarf stars being one of the order of trillions of years, could there be any population of, I think that says of, population 3 red dwarf stars? Maybe I should ask first, do we think red dwarf stars were formed right after the Big Bang to be a part of the population 3 stars? Thank you for considering my question, and always informative podcast. From Ron.
Thanks, Ron, and greetings to upstate New York. Yeah, that's another. They're all great questions that we get on Space Nuts, and it's a very intelligent one as well. And just to sort of give the backstory of this, population 3 stars, and it's usually written as a Roman 3, are stars that they're what we think of as being the first stars to form in the universe, back probably within the first 200 or 300 million years of the Big Bang, which we believe happened 13.8 billion years ago. So what would signify a population 3 star? It would be a star whose spectrum, when you analyze its light, reveals only the presence of hydrogen and helium, because they were the elements that were predominantly produced in the Big Bang. There were a few other things produced in very, very small quantities, like lithium, but really it was mostly hydrogen and helium that were produced in the Big Bang. And so population 3 stars will be stars that only show the signatures of those chemical elements in their spectrum. We haven't actually found any yet. We found some that look very nearly like population 3 stars, but they still have a little trace of iron in them, the ones that have been found. And iron is formed in the interior of stars, and so you know that anything that shows up iron is not the first generation of stars ever to exist, because other stars have been there first and have formed the iron. So population 3 stars are a bit of a holy grail, actually, trying to find them. I've worked with people here in Australia whose sole scientific mission has been to find population 3 stars, and they've come pretty near it with these very early, what we call metal poor stars. Metals, unlike the way we think of metals in everyday life, things that contribute steel and brass and stuff like that. Metals are anything other than hydrogen and helium to an astronomer. It's a very curious expression. So metal poor stars are ones that don't have much of anything other than hydrogen helium. So cutting to the nub of Ron's question, though, we think the very first generations of stars to form in the universe were not red dwarfs. We don't think they were dwarf stars at all. We think they were very massive stars, perhaps 20, maybe even up to 100 times the mass of the sun, that had very short lives and exploded, within perhaps less than 1 million years. Such a short life. That remember, our sun is 4.5 billion years old, and it's in its sort of midlife, not a crisis, but a midlife time. So red dwarfs probably did not form in the early universe, and in any case, what categorizes a red dwarf star is actually the fact that it is that it has seen many generations of stars before it, because they're rich in all kinds of different chemical elements, not just hydrogen and helium. They are basically, cool stars which show the characteristic signatures of all sorts of things, even molecules. I think some molecules don't usually exist in stars because they get torn apart. The atoms get torn apart by the heat. But I think red dwarf stars have some molecular signatures as well. So the answer is, I think, no. Red dwarf stars weren't formed right after the Big Bang, and there probably aren't any population 3 red dwarf stars. But you're absolutely right that the lifetime of red dwarf stars is very, very long, maybe up to trillions of years, as you've suggested, Ron. Thanks very much for the question.
Very interesting indeed.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our very last question is another great question from Jake Johnston. He says, "Hey, Space Nuts, quick question. While it is totally possible that there is no life in our solar system except for on Earth, if you had to guess where the most likely other place in our solar system is to find either current or ancient life, what would you choose? Titan? Mars? Thanks."
Let's give you a shot at this one, Heidi. What do you think the answer to that would be?
Oh, I was actually thinking in my head of playing a joke and just saying some random planet and then going, "Oh, oops, he must have meant this for you." I don't know. I really think that it's gonna, for some reason, I think there's probably something on a moon somewhere, because I'm just imagining primordial solar system, everything's crashing into each other. And when that matter ends up on a planet, it's getting churned through its core and getting heated up, and everything that maybe existed, even bacteria, is just getting cooked and destroyed. But on a moon, it's not getting that turnover. So I would assume, and this is with my background, not in this at all, I would assume that we would find something on a moon.
I think you're right, actually. So I guess the most obvious places to look, first of all, Mars. Mars, we know, has been warm and wet in the past. We know that it was warm and wet at a time when the first living organisms were forming on Earth. So if all you need is the right atmospheric conditions, well, they were there on Mars. And so Mars may show signs of ancient microbial life. Unfortunately, we don't at the moment have the wherewithal to find it. We've got samples of rocks and soil that have been taken by the Perseverance rover on Mars, which are stashed away for a future mission to go and collect them. Sadly, that mission is a bit in doubt at the moment because it's turned out to be very expensive. But there may be evidence on Mars. But you're absolutely right that some of the moons of the solar system are perhaps the next on the list because, first of all, and this is the one that's really the poster child of looking for life on moons in the solar system, is Europa. Europa, one of Jupiter's moons, which we know has a rocky core. It's got a liquid water ocean over that core, and that is sealed in by a layer of solid ice on top of it. And we have seen evidence of geysers of ice crystals coming through that layer of ice because of cracks in it. There is evidence as well that there are quite complex carbon-containing molecules on the surface of Europa. It's got a reddish-brown color, which looks as though it's the effect of sunlight on and solar radiation on these carbon-containing molecules. So the ingredients for life might very well be there. Likewise, further out in the solar system, Enceladus, Saturn's moon, which was explored by Cassini, that definitely has these geysers of ice crystals because we've seen them. And in fact, Cassini flew through them and measured some of the contents of them in terms of, it's mostly water ice, but there's also molecular hydrogen and some other really interesting ingredients that suggest that there are geothermal vents down at the bottom of Enceladus's oceans. Maybe that is where life could have kicked off. We think life might have kicked off on Earth down in hydrothermal vents, maybe on Enceladus too. And, Dean mentions also Titan. I beg your pardon, Jake. I'm sorry, Jake. The wrong name there. Jake also mentions Titan, which is another of these ice worlds with the same sort of structure and a liquid ocean, but it's also got these lakes of methane and ethane, liquefied natural gas. The only place we know anywhere in the universe other than Earth where there's liquid in equilibrium with an atmosphere, and Titan has a thick atmosphere, mostly carbon dioxide, but hydrocarbons in there as well. So these are all great candidates for living organisms. And if I had to pick one, let's go with Titan, because I think you get two shots at it there. There might be water-based life in the oceans underneath the surface, but there might also be some weird carbon-based life in the liquid natural gas lakes and seas on Titan. And we might find that when the Dragonfly spacecraft visits Titan later in the decade.
These are all very exciting. I mean, there is just so much happening in space right now. Every single week, we are closer and closer to new breakthroughs and new discoveries. And I'll even share a program that I'm a part of that anybody who is a high school, or like if you're in high school, if you're doing your undergrad, graduate, or early career professional, you can join this too. It's called the L Space, so L''Space program. And it is a competitive proposal writing program where they select different individuals. So you can apply. I'm in the summer program right now, but you can apply for the fall program. But all of us got put into different interdisciplinary teams, and we are going to be coming up with a proposal that is going to address one of NASA's gaps. And they have a whole training on how to write proposals the way NASA wants them written, and the taxonomy of everything they're looking for and the gaps that need to get filled. But the cool thing is that the proposals that we come up with, one of them will be selected as the winner, and the winner will get thousands of dollars of grant money, and it will probably go on to become a real project. So if you are an engineer, even a high school student or early career professional or anyone in between who feels like you have a lot of good ideas for discovering these kinds of things. Like, I've been co-hosting now for a while, and I've seen how smart you guys are. So I would really encourage you to all get involved and use your creativity to help push humanity forward into the stars, because every single one of you has something to add. And never, ever, ever let imposter syndrome get in the way of that, because every creative mind adds something to all of this. And that's my rah-rah for this week.
Remind us again what the program's called, Heidi?
It's L Space. So it's an L' and then SPACE. And the program that I'm in, they have several different programs. So I'm in the proposal writing. So NPWEE, NASA Proposal Writing Experience something. They love acronyms. Yes. But yeah, L Space, and you can look that up. I can probably send the link to that to you guys to post in the link and the description of this episode if anybody is interested in adding to their contributions into space.
Fantastic. Great program. And I look forward to checking it out on the web.
Absolutely. Well, thank you so much, Fred. This has been another wonderful Q&A session of Space Nuts. We'll catch you all. We'll catch you all next week. Bye for now.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.